So in the meantime, my name is Elica Kyoseva, and I'm Director of Quantum Algorithm Engineering. Okay. And the title of today's talk is AI for Quantum Computing. I will give an overview of NVIDIA and our efforts in quantum computing. And also I will touch on some points that we covered in a recent paper which we released on the archive last month. So what about NVIDIA and how are we engaged and why are we engaged in quantum computing? Well, NVIDIA invented the GPU, the graphics processing unit, about 25 years ago. And since then, our technology, GPU supercomputing, was used to revolutionize a few computing revolutions. Right. So first was scientific computing, and how it was done was when NVIDIA actually released the CUDA programming platform. And scientists were able, whoever was able to program in C++, was able to actually use GPU computing for their matrix manipulations and other scientific workloads. This really led to the development and to the acceleration of a lot of scientific computing and to the inclusion of GPU in almost all of the supercomputing centers in the world. In about 2012, it was also recognized that GPUs are very powerful when it comes to deep learning. And their adoption for deep learning processes and tasks really also accelerated that field. In 2016, there is already a very famous anecdote of our CEO, Jensen Huang, actually hand-delivering a DGX system to OpenAI when it was actually recognized that GPUs will be very useful for generative AI. And this enabled the AI revolution that we are all experiencing now. So what is the next computing revolution? We very much believe that this is the quantum computing revolution. That's why we are all here today. And NVIDIA's role is really to provide, again, AI supercomputing to all of the researchers that are working in quantum computing across the whole stack and to enable solving the challenges which quantum computing faces. And this is a question that we get asked all the time and every few months. So it always makes sense to make it clear that NVIDIA is not building a quantum processing unit. We are not interested in developing any type of quantum hardware. But how we position ourselves is actually that we're building all accelerated quantum supercomputers. So how do they look like? So this is how an accelerated quantum supercomputer of the future looks like, and this is how a useful quantum computer looks like. It is an integrated AI supercomputer with different QPUs. The QPUs can have a different modality. We are staying very hardware agnostic. And it's also important to realize that maybe there is more than one quantum computer that is integrated in this quantum supercomputer. So our framework actually supports MQPU, so multi-QPU backends, and it is very important that we can connect the AI supercomputer to the quantum computer with the most efficient networking and architecture. So this kind of a supercomputer of the future, quantum supercomputer, includes QPUs, AI supercomputing, and different networking, which is actually equally important. So this is the vision, and this is where we want to go to. But this is where we are today. Of course, we have a lot of developments, a lot of announcements, and really every year we see steps towards realizing the accelerated quantum supercomputer of the future. But there are many technological challenges that we need to solve before that. For example, infrastructure challenges. We see globally a lot of supercomputing centers are actually becoming more and more interested to integrate with the QPU, because how we connect a QPU to a supercomputer remains a very big open question, and it requires a lot of know-how, a lot of expertise, and this is also something that we are very much interested to solve, how to figure out the best low latency interaction, close coupling of QPU and AI supercomputers. Another open question, as also we heard from the talk before me, is implementing quantum error correction. Quantum error correction at scale will require a lot of classical compute, and we want to make sure that we provide the tools to all of the researchers that are working on error correction to do this in real time and with the required bandwidth. Then hybrid algorithms. I always like to say that all quantum algorithms, all quantum applications are hybrid. And the reason for that is that when you work in industry, you will always use a classical supercomputer to support your application workflow. And then the quantum computer will be only like an accelerator. So every application will indeed be hybrid. And we can use AI supercomputing for maybe pre-processing, post-processing, control of quantum computers, maybe hardware design of quantum computers. And the last open question, which I also already touched on, is better quantum hardware. So we need to design qubits with better fidelities. And all of these open questions and challenges in quantum computing can actually be met by using AI supercomputing. So this is how we are engaged in the quantum computing space. So we have a product. There's a lot to unpack on this slide, but we have a product, and the name of this product is Q2B24. It is a programming framework. It is a programming platform for hybrid computation. So it supports, on one hand, classical simulations of quantum circuits, and it interacts, of course, very natively with AI supercomputers like the DGX SuperPod. And on the other side, it also supports quantum backends. And the quantum backends can actually be running on actual quantum computers. And we have over half a dozen already backends from QPU providers. And of course, this list expands as we speak. But we also have this SDK, Q-Quantum, which is accelerated, and it is best-in-class simulator of quantum circuits when one wants to simulate a quantum algorithm before they actually implement it on a quantum computer. On top of that, on top of Q2B, we also have NVIDIA Quantum Cloud, where people can actually go, even if they don't have on-prem access to GPUs, they can have access and they can do discovery simulations and discovery of applications with Q2B. And we also just recently, in November, announced Q2QX, which is our first libraries in quantum computing for Q2Q, which cover two types of libraries. One of them is solvers, and the other one is QEC for quantum error correction. Q2Q is open source, and we like to work with absolutely everyone in the community. I think this is very important to say. We don't think that we'll be able to solve all of the challenges that quantum computing faces, but what we believe is that we can put the best tools in the hands of the researchers that will be able to solve these challenges by themselves. So we are very interested in exploring AI for quantum computing, and we looked at the whole computing stack and tried to analyze and to find all of the bottlenecks that AI can solve. The results of that overview, let's say, was published in this paper, which we put on the archive last month. And the first point that we looked at, I invite everyone to have a look at that paper, of course, is that we can use AI supercomputing to design better quantum hardware. So, for example, when quantum hardware providers design their QPUs, it takes a lot of iterations, and it will be really expediting the process if we are able to simulate the design before we actually go and fabricate it and do experiments with it, etc. For that, of course, we need to be able to simulate open quantum dynamics, we need to be able to simulate different types of noises, etc. So there have been some works already which showed that we can use machine learning for Hamiltonian learning. And also we can use machine learning for quantum device characterization. So these include tuning, qubit tuning, characterization, improving also the measurements of qubits, etc. And to enable research in that area and to help researchers really use AI supercomputing natively for these types of open challenges, we released NVIDIA quantum dynamics simulations, which guide the design of qubits to reduce the error rates and extend coherence times of QPUs. And it can help providers really build better quantum hardware. We designed this functionality in collaboration with Google Quantum, and with them we had a big result just last month at Supercomputing, where we were able together with them to simulate the largest quantum processor dynamics, so dynamics of a quantum processor of 40 qubits. So I invite everyone that is working actually on quantum hardware design and is interested in improving the performance of QPUs on the qubit level to have a look at that functionality. Another thing that we can improve, of course, is algorithms, and in fact, hybrid algorithms with AI, supercomputing. So how AI can actually help in that space is by helping prepare the circuits, so circuit synthesis. It can also help us compile the circuits, which is, again, an open problem, and it can also help in post-processing. So if we look first, what we consider, we call it pre-processing. We can actually use AI to help us compile and to solve the circuit synthesis problem. And there have been already works in that, because compiling an n qubit unitary into the native gates of a particular QPU is actually a hard problem, and it grows exponentially with the number of qubits. So there have been already some works in reinforcement learning where they can be used to compile a large unitary. And most recently, earlier this year, a work that came out that we were actually also involved in, it's called the GPT-QE, which stands for the Generalized Transformer Network for Quantum Eigensolver. And it uses exactly the same transformer model like GPT, like OpenAI's GPT. But here, what we do is actually we use it to generate shallow circuits that find the ground state of a particular chemical system. And this was, in fact, the first work where we used an AI model to generate a useful circuit that does something that we trained it for. Another way that we can use AI for pre-processing is by doing an initial parameter generation. So this, in fact, means doing a parameter transfer between different circuits for different use cases. And it has already been successfully applied in that reference number 2. And another way that has already been done as well, and another possibility is to do state prep. So we use reinforcement-based learning methods for state preparation of a quantum circuit. Another thing is for post-processing. So we can, there has been work already on machine learning for qubit readout. And convolutional neural networks were already used with the neutral atom quantum processor. And there it was shown that there was a reduction of the error for the measurements of the qubits with 56%, with up to 56%, and up to 32% for single and multi-qubit readout errors. It is also possible to do real-time, faster readout, which is in fact a cornerstone for quantum error correction. Another way that AI supercomputing can help for post-processing is also with error mitigation. And it is possible to show that machine learning quantum error mitigation reduces with 25% the computational resources that are required. So reducing the number of times we need to run a circuit compared to when we don't use machine learning for quantum error mitigation. Another part of the stack that can be improved is by scalable control infrastructure. We have, in fact, a reference system in that, which is called DGX Quantum. But this is a system that can really control the quantum chips, and it can optimize the complexities of the control pulses and all of the things that go around controlling and managing the quantum chip. I will not go into more details on that because there will be another talk tomorrow that will cover that. And also for quantum error correction. We know that we can use AI to help us discover better error correcting codes and for decoders. So we consider that, of course, as two areas. So one of them is AI for code generation, where we train the AI model to generate a code with particular properties. And of course, in the long term, we are interested to generate code for a particular type of hardware. So by including the conditions and the particular noise and all of the other native gate sets and all of the other properties of a particular hardware. And the other way that AI can help in quantum error correction is AI for decoders, where the result of syndrome measurements are in fact decoded by machine learning models. If you are interested in that, there is a talk tomorrow by Sam Stanwyck, so not tomorrow, on Thursday at 2 p.m. And the title of the talk is AI Supercomputing for Quantum Error Correction, where he will go into much more details about that. So then the last thing is also, of course, post-processing tools where we analyze the outcome and the measurements of quantum experiments, mitigate the errors, elucidate observables, and everything. So this is the QR code to the paper, and I invite whoever is interested to have a look at it. But as I mentioned, we are not going to solve all of these problems by ourselves. What we are trying to do is, in fact, to provide the tools to the researchers that work in these areas to use them and to really use all of the AI supercomputing resources available globally to address these challenges. So in terms of the post-processing tools, of course, this is classical data. So there are a lot of accelerated libraries that are available from NVIDIA. For implementing quantum error correction, we just released a library, as I mentioned, which is called CUDA-QX QEC, and I invite error correcting scientists that work on that to have a look at this library. For the scalable control infrastructure, we have the reference system, which is DGX Quantum. It's in collaboration with Quantum Machines, and this is the first architecture which showed low latency coupling of an AI chip, AI supercomputer with a quantum chip. For hybrid algorithms, we released another library, which is called CUDA-QX solvers. For the moment, it has all of the basic solvers like VQE, Adapt VQE, QAOA, and we are also adding a lot of functionalities around using AI to generate circuits like the GQE method, which I mentioned before. And for the quantum hardware, this is the CUDA-Q Dynamics functionality, which we developed in collaboration with Google, which I also described earlier. CUDA-Q is available for free on GitHub, and this is the QR code to our GitHub link page. We work very broadly with the whole ecosystem. We engage with quantum hardware builders, with simulation frameworks. We work with other simulation frameworks, and we are very happy to accelerate them as well, with system builders and integrators. Of course, quantum software and application startups, big companies as well, research centers, and cloud service providers. If you don't see your logo on that list, please come and find us and talk to us, because we are very much happy to enable everyone to do their job. And before I finish, I would like to highlight a conference on that topic, which is going to take place in March in Denmark. The topic of the conference is AI for Quantum, Accelerated Quantum Computing with AI. It is funded by the Novo Nordisk Foundation. And we are very closely working with Copenhagen and with Denmark, the whole ecosystem there, based also on their recent announcement and launch of the Gefion supercomputer, which is an NVIDIA supercomputer for research, for really bringing value to the Danish economy. And quantum computing is one of the use cases that they will be exploring. So AI and quantum computing are very big in Denmark. That's why the Novo Nordisk Foundation is organizing this conference. And please apply to come and attend and speak if you're interested by the end of the month. And with that, I would like to finish. Thank you very much.